All right, let's get straight to it. We're not talking about just another component today. This is the strategic briefing. This is for the teams that are tired of just competing in Formula Student and are ready to start setting the pace. This is your blueprint to dominate. So, you ever look at the results and wonder, how do the same teams end up on the podium year after year? What's the secret? Well, I can tell you, it's not luck. And you know what? It's almost never about who has the biggest motor. The real gap, the secret weapon, is a massive technological advantage in one single place: the motor control unit, the MCU. When you look at the grid, it really breaks down into 3 different tiers of technology. You've got your entry-level Tier 3 teams, right? They're using off-the-shelf industrial inverters. They work, they're reliable, but they're a total black box. You can't optimize them. Then you have the advanced Tier 2 teams. They're building their own stuff, usually with a standard MCU, but they always hit a performance ceiling. But the teams that win, the ones on the podium, they aren't even playing the same game. They're in Tier 1. They've made the jump to FPGAs and Silicon Carbide, and that changes everything. So this brings every ambitious team to a critical decision point, a real fork in the road. You can follow the slow path, trying to squeeze out tiny incremental gains year after year, or you can decide to leapfrog everyone, go straight to the Tier 1 architecture that's already winning. What we're doing here today is laying out the exact blueprint for making that leap. So let's dive in and see what it takes. Okay, here's the plan. We're going to look at the 3 core pillars of a winning system: the brain, which is all about computing, the muscle, the power electronics, and the nerves, the communication network. And then we'll cover the step-by-step process to put it all together so it actually works on race day. All right, first up, the brain. This is probably the most important piece of the puzzle. This is where you fundamentally break away from the processing bottleneck that holds back, I'd say, 90% of the teams out there. And the weapon of choice for the top teams is something called a Zynq system-on-chip, or SoC. Now, what is that? The simplest way to think about it is you get 2 brains in one. You have a powerful ARM processor, that's your software brain for complex tasks, but fused right onto the same piece of silicon, you have an FPGA, that's your hardware brain for pure raw speed. This combination is the absolute key to unlocking true real-time control. And this is how you use those 2 brains. It's a philosophy, really. Fast loop versus slow loop. It's a divide and conquer strategy. You don't ask one processor to do everything. Instead, you assign tasks based on speed. Anything that has to happen instantly, like current control or safety checks, you hardwire that into the FPGA. That's your fast loop. Everything else, like speed control, communications, temperature monitoring, that can run on the ARM processor. That's your slow loop. So let me be absolutely clear about what we're talking about here. Those critical functions, the really complex math for field-oriented control, the safety interlocks that stop you from blowing up the inverter, they're not running as software on the FPGA. They are implemented in the hardware. The algorithm literally becomes the circuit. Think about that. There's no operating system, no software lag, no jitter. It's pure, predictable, lightning-fast execution. And here's the payoff. You get a total loop latency of under 10 microseconds. Let me say that again. Under 10 microseconds from reading a sensor to changing the power output. That speed is what lets you push your control frequency past 100 kilohertz. And why does that matter? Because the high-performance motors you use in racing are incredibly low inductance. They react so fast that if your control system is any slower, you simply can't control them properly. You're just chasing the motor, never truly in command. Okay, so we've got a world-class brain. Now we need the muscle to back it up. Because having a super fast controller is completely pointless if your power stage is slow and sluggish and can't keep up with the commands. And that muscle is Silicon Carbide, SiC. Look, this isn't just a small upgrade from traditional silicon. It is a completely different beast. It's a game changer. These things switch faster, they handle way more heat, and they're incredibly efficient. What that means for you is you can build an inverter that is way smaller, way lighter, and packs a much bigger punch for its size. Now, here's a critical detail that trips up a lot of teams, a classic rookie mistake. They see they have a 600-volt battery pack, and they think, oh, 650-volt components are fine. No, they are not. When you switch silicon carbide that fast, it creates massive, violent voltage spikes. If you don't have enough headroom, those spikes will kill your components. Using 1200-volt parts isn't optional. It's the non-negotiable safety margin you need to actually use silicon at the speeds it was designed for.
And speaking of that violent switching, think about the electrical noise it creates. It's like a hurricane of electromagnetic interference inside your inverter. To control this power, your gate driver, the little chip that tells the SiC when to turn on and off, it needs to be basically deaf to all that noise. The spec for this is called Common Mode Transient Immunity, or CMTI, and you absolutely need a rating of over 100 kilovolts per microsecond. If you don't have it, that noise will corrupt the signals from the brain, and boom!
Okay, we have the brain, we have the muscle. Now we need the nervous system to connect it all together. And for a four-wheel drive car, this is so critical. If you want to use things like torque vectoring to stay at the absolute limit of grip, every single motor needs to get its command at the exact same time. And I don't mean pretty close, I mean exactly the same time. So when you look at the options, the choice becomes crystal clear. You've got CAN FD, which is good for some things, but for your primary control network, the one that's doing real-time torque vectoring, it has to be EtherCAT. Look at the sync accuracy. It's not even a contest. That's because EtherCAT processes data in hardware, on the fly, as it passes through. CAN has to stop and think about it, using software. So yeah, keep CAN FD around for sending telemetry back to the pits, but for vehicle control, it's gotta be EtherCAT. And this is the number that makes all the difference. Less than 1 microsecond of timing error between all four corners of the car. That's what EtherCAT's distributed clocks give you. That is the difference between a car that feels perfectly planted, like it's glued to the track, and a car that feels nervous, unpredictable, and is always trying to spin on you. It's all about that timing. So you've got the best brain, the best muscle, the best nervous system. Fantastic. Now, how do you actually make it all work together without a bunch of expensive, soul-crushing explosions? The answer is process. A rigorous, disciplined, non-negotiable process. And that process is called the V model. It's a structured path. You start safe, in a pure software simulation, just to make sure your control logic even makes sense. Then, and this is the absolute key, you move to hardware in the loop, HIL. This is where you test your real physical controller against a powerful simulation of the motor and inverter. This step is a mandatory gateway. You do not pass this step, you do not go to the dyno, period. Only after it's perfect in HIL do you move on to the dyno and finally the track. Seriously, let this quote sink in. HIL is not just a nice to have. It is the secret to reliability. It's how top teams find 90% of their bugs in a totally safe environment. It's how they avoid destroying those incredibly expensive SiC modules during testing. If you want to know why some teams always finish the endurance event and others don't, this is it, right here. So there you have it. That's the blueprint for victory. It's the whole package. A Zynq SoC for the brain, doing hardware-accelerated control. 1200-volt SiC MOSFETs for the muscle, giving you insane power density. An EtherCAT network for the nerves, for perfect synchronization. And all of it is built on a foundation of the V-model process with mandatory HIL testing. It's not just a collection of good parts, it's a complete, cohesive system designed to win. Which brings us to one final and I think very important question. Following this blueprint, it's not just about winning a competition. It's about giving yourselves a masterclass in the exact technologies that are defining the future of the entire car industry. We're talking heterogeneous computing, wide-bandgap power electronics, software-defined vehicles. This is the real deal. So the question you have to ask yourselves is, are you just building a car to compete, or are you building engineers who are ready to lead?